Hey guys, this is the notes here for, as you can see, 11.3 combinations. In the mathematical context, the word combination is used to figure out how it's another way to count, but it's a way to calculate by using factorials and some multiplication, obviously, to see how many different outcomes there are in a situation where it doesn't matter what order the things I pick are in. Remember, the permutation is when the order matters. Combination is when it doesn't. This note set starts out with the simple question, is it a permutation or a combination? We're not going to solve these. We're just going to decide if it's a permutation or a combination. Remember, permutation, the order matters. Combination order doesn't matter. See, combination, group of items taken without regard to their order. No item is used more than once. Order makes no difference. Again, combination. Permutation is when the order matters. So let's see. 6 students running for student government: president, vice president, and treasurer. Student with the greatest number of votes becomes president, second highest becomes vice president, and third largest number of votes will be treasurer. How many different outcomes are possible for these 3 positions? Well, again, the order matters needs to be taken loosely, but the fact of the matter is this is a permutation because it does make a difference, right? Like, the jobs I will do will be different based on if I'm president versus like secretary, or president versus vice president. The job, my duties will be different. Therefore, it's considered like the order matters. So permutation on this one. 6 people are on the board of supervisors for your neighborhood park. A 3-person committee is needed to study the possibility of expanding the park. How many different committees could be formed from the 6 people? Notice how this one is just saying 3 people to form a committee to talk about the way the park, what are they talking about? Expanding the park. So a 3-person committee, so it doesn't matter what order they're picked in. This is a combination because it's, again, all 3 people have the same job. It doesn't matter what order they get picked, they all have the same job, and it's to discuss the possibility of expanding the park. So that one's a combination. The next one, let's see here, is Baskin Robbins, 31 different flavors of ice cream. One of their items is a bowl consisting of 3 scoops of ice cream, each a different flavor. How many such bowls are possible? Well, this one is a combination also because it doesn't matter what order the flavors get picked in. Right? If I, chocolate, vanilla, strawberry, doesn't matter which one I pick first. If I have those 3 flavors, it doesn't matter if I go chocolate, vanilla, strawberry, vanilla, chocolate, strawberry, strawberry, chocolate, vanilla. It doesn't matter what order those flavors get picked in. The fact of the matter is, any 3 flavors, as long as it's those 3, it won't matter what order. So again, combination. This one here, practice 1A. Let's see. How many ways can you select 6 free videos from a list of 200 videos? This is a combination because it's, again, the order won't matter, right? If I pick 6 movies, right, get 6 free movies, and I pick 6 movies to get for free, it doesn't matter which one I pick first and which one I pick last. I'm just going to receive 6 free movies, so the order in which I pick them doesn't matter. Combination, not a permutation. The next one, in a race in which there are 50 runners and no ties, in how many ways can the first 3 finishers come in? Well, this matters, right? First place isn't the same as second place. Second place isn't the same as third, and so on. So this is a permutation. Again, the order does matter here. First, second, and third are not the same thing. So here you see the combination symbol NCR instead of NPR. It's NCR. Means the number of combinations of N things taken R at a time. Combination N choose R. So again, N is the total number of things I'm picking from. R is the total number of things I'm picking. And you can see it's different than the permutation formula by adding in this extra r factorial. Without that r factorial there, it's the exact same thing as the permutation formula, but throwing in that r factorial, which represents that number, it is not the same. It's similar as the permutation one, but not the same. This formula tells me how many possible outcomes I have in a scenario where the order in which I pick doesn't matter, aka a combination. So let's see here. A 3-person committee is needed to study ways of improving public transportation. How many committees could be formed from the 8 people on the board of supervisors? So this is going to be 8C3, picking 3 people from 8 total, where the order in which they get picked doesn't matter because it's just a 3-person committee to discuss ways of improving public transportation. All 3 people have the same role. Order doesn't matter. So this one again is a combination. And if you look back to the formula, right, you'll have 8 factorial here over 8 minus 3 factorial, but then times another 3 factorial there. So the calculation will just be a little more complicated than the permutation one. Basically, you're going to divide by having this extra number, you're dividing by a larger number. So when it's a combination, there's going to be less possible outcomes, because back to like the ice cream example, chocolate, vanilla, strawberry is the same thing as strawberry, chocolate, vanilla. It's still the same 3 flavors. Doesn't really matter what order they get picked. 8 minus 3 is 5, and then we have that other 3 factorial. So let's do this. Let's cancel the 5. Right, if we cancel the 5, then on top I only have 8 times 7 times 6 left. Anything 5 or less cancels. And then here 3 factorial, 3 times 2 times 1. And then we can kind of cancel as we please here, right? I can cancel the 3 here with the 6. And I can now cancel this 2 with this 2, and then they've canceled everything. All I have left is 8 times 7. So there's 56 different ways that a 3-person committee can be selected from a total of 8 people. 56 ways. So this next one, if you read it, you volunteer to pet sit for your friend who has 7 different animals. How many different pet combinations are possible if you take 3 of the 7 pets? Well, it basically is kind of telling you it's a combination, but you would also know it is because, let's see, there's 7C3, right? 7 animals, we're picking 3. And it doesn't matter what order they get picked in, right? Like, let's just say they're all different types of animals. If you pick like dog, cat, rabbit, it doesn't matter what order you pick those in, right? If you pick dog, cat, rabbit, or rabbit, cat, dog, that's essentially the same group of pets. So again, the order in which they get picked doesn't matter. So this is our combination formula, right? So we're going to use 7 factorial, 7 minus 3 factorial times 3 factorial, and we're just gonna once we are good with the formula, it's just the same skills to solve it, right? 7 minus 3 is 4. There's a 3 there. Let's cancel the 4, leaving us with 7 times 6 times 5 on top. Everything 4 or less cancels, remember that. But the 3 factorial, 3 times 2 times 1. We could cancel, well, really the 3 and the 2 with the 6, right? 3 times 2 is 6, so we could do that. We can cancel 3 times 2 and the 6. Leaving us with just 7 times 5 for 35 ways, 35 different combinations of 3 pets taken from 7 total pets. Next one here. In poker, a person is dealt 5 cards from a standard 52 card deck. The order in which you are dealt the 5 cards does not matter. So they're telling us it's a combination, and so we'll just calculate that one using the combination formula. 52 card deck, 5 cards, so 52C5. We'll have 52 factorial over 52 minus 5 factorial times 5 factorial. So 52 minus 5 is 47. Bring over that 5 also. We're going to cancel the 47 factorial, and everything 47 or less is going to cancel on the top. So 52 times 51 is 50 times 49 times 48. Right? Anything 47 or less cancels. And then 5 factorial. 5 times 4 times 3 times 2 times 1. And you're gonna want to cancel here. Definitely makes sense to cancel some stuff. So let's say we cancel the 5 with the 50 to get a 10 there. We can also cancel the 4 with the 48 to get 12 there. We can cancel this 2 here with this 10 and get a 5. And I believe we can also cancel this 3 here with the 51. 51 divided by 3 is 17. So now I can just, now I've canceled everything here. Now I can just multiply 52 times 17 times 5 times 49 times 12. And that'll give me the total number of combinations here. So making this calculation, you can see there's nearly 2.6 million different poker hands possible. How many different 4-card hands can be dealt from a deck that has 16 different cards? Again, a combination. The order doesn't matter, but right, combination taking from 16 cards, picking 4. How many different ways can that be done? Right, so 16 factorial over 16 minus 4 factorial times 4 factorial, and let's go ahead and simplify this. 16 minus 4 is 12. Times 4. We're gonna cancel that 12. Hopefully you're good with that. Cancel the 12, and then on top, anything 12 or less will cancel, and here on bottom still have that 4 factorial, and I'm going to start canceling. 16 divided by 4 is 4, 15 divided by 3 is 5, 14 divided by 2 is 7. I've now canceled everything on bottom, so I just have 4 times 5 times 7 times 13. Well, 4 times 5 is 20. 20 times 7, that's 140, and then 140 times 13, 1,820. 1,820 different hands, 4-card hands, picking from a 16-card deck. Okay guys, so these last couple problems here, they do involve a couple of combinations mixed with the fundamental counting principle. I'm just going to kind of show this real quick, this diagram from the book. It says this is what the problem says, there's 54 Republicans and 46 Democrats in the Senate, according to the problem, and we're choosing a committee with 3 Republicans and 46 Democrats. So we're going to figure out how many different ways we can choose 3 Republicans from 54 Republicans, you see 54C3, and how many different ways we can choose 2 Democrats from 46 Democrats, 46C2, so it's 2 different combinations for that. And then we're going to multiply this times that to get the, that's the fundamental counting principle aspect. So it's combination for Republicans, combination for Democrats, and then we multiply the 2 totals together to get the total different ways that we can select a committee of 5 people with 3 Republicans and 2 Democrats. So, again, it's 54 Republicans and 46 Democrats. How many committees can be formed if each committee must have 3 Republicans and 2 Democrats? So it's 54C3 for the Republicans. How many different ways you can pick 3 from 54? And we're going to multiply that by the total number of ways we can pick from 46 Democrats. How many ways we can pick 2 different ones. So we have to calculate for both combinations and then multiply those totals together. as I was, showing you the image from the book. So we have, I suppose we should have maybe calculated this separately, but either way, the first one, 54 factorial over, remember, all these, the order doesn't matter because we're just picking 3 Republicans to be on a committee. They all have the same job, basically, so it doesn't matter what order we pick them in. And 2 Democrats, same scenario. It doesn't matter what order we pick them. They're just on the committee. And over here, another 3 factorial, and then times. Over here, it'll be 46 factorial divided by 46 minus 2 factorial times another 2 factorial. So, hopefully we'll be good with space here. So the first one, 54 factorial over 51 factorial times 3 factorial. And over here, 46 factorial. 46 minus 2 is 44. And then a 2 factorial. And then, as we've been doing, we're going to cancel the lesser of these 2 factorials. So cancel the 51, leaving you with 54 times 53 times 52. And on the bottom, we still have the 3 factorial, so 3 times 2 times 1. And then over here is pretty much the same thing, right? We're going to cancel the 44, leaving us with 46 times 45 in the numerator, and then simply 2, or 2 times 1 in the denominator. And before I wrap this up, I'm going to cancel some stuff here. Let's see. I know 2 goes into 52, right? That's going to be 26. Does 3 goes into 54, actually. 3 goes into 54 18 times, so that's done. And here, just cancel the 2 with the 46 to get a 23. And, you could just multiply this all the way through, because once I calculate this and then this, I don't have to calculate them separately. So I could just go 18 times 53 times 26 times 23 times 45, and that'll be the total number of ways that a 5-person committee can be selected, where it has 3 Republicans choosing from 54 and 2 Democrats choosing from 46. So let's see what that is. 18 times 53 times 26 times 23 times 45. And that's a huge number. 25,672,140 different committees. So, let's see. 25,672,140 different committees are possible here. So this next problem is the same as the previous one. The numbers are different though. It's 50 Democrats this time and 49 Republicans, and each committee must have 3 Democrats and 2 Republicans. So anyhow, let's see. So we're picking from 50 Democrats, we're picking 3, so 50C3. And from 49 Republicans, we're picking 2, so 49C2. And it might make more sense to calculate these 2 things separately. If that makes more sense to you, you can do that. Just remember, though, you are going to multiply the totals by each other. It's calculate how many different ways you can get. Again, 3 Democrats from 50. That's a combination, of course. The order doesn't matter. The 3 picked will have the same job. Here, the 2 Republicans picked will have the same job. And again, so picking 2 from 49. And again, if, the total number of different ways you can select these 3 from 50. And then the total number of different ways you can select 2 people from 49, right? And once you get those 2, it's fundamental counting principle, as in the last one. It's if you multiply this times this, that's using the fundamental counting principle to see how many total different committees there are. So the 50C3, right, that's 50 factorial over 50 minus 3 factorial times 3 factorial. And then the 49C2 is 49 factorial over 49 minus 2 factorial times 2 factorial, right? Again, just using my combination formulas. So here, I'll have 50 factorial, divide by 47 factorial, 3 factorial. Cancel the 47 on top, right? Anything 47 or less is gone, so 50 times 49 times 48 is what we have there. On bottom, 3 factorial, 3 times 2 times 1. We can cancel the 3 with the 48. It goes in 16 times. We can cancel the 2 with the 50. It goes in 25 times. And that's it. Now we can calculate 25 times 49 times 16. 19,600 different ways. 19,600 different ways to select 3 Democrats from 50 Democrats. Then here, 49 factorial. 49 minus 2 is 47 factorial times 2 factorial. And same as what we've been doing, we're going to cancel out the 47, leaving us with just 49 times 48 in my numerator. 2 times 1 in my denominator. Cancel the 2 with the 48. 48 divided by 2 is 24. And 49 times 24, 1,176. 1,176 different ways to select 2 Republicans from 49 Republicans. And then the last thing is multiplying these two together. So again, 19,600 ways to get your Democrats in this context, in this problem. 1,176 different ways to get the Republicans. So how many total different 5-person committees based on this context? Well, you can multiply. Again, the multiplying here would definitely be fundamental counting principle. So again, combinations and fundamental counting principle. 19,600 times 1,176, and it's 23,049,600 different committees. 23,049,600 different committees.